Yeah, we got that last term. You didn't notice? It was about, yeah, it was a couple weeks before the end. You got so used to no clock. I know. Me too. Okay, so basically the essence of what we're covering today is simple harmonic motion. So waves show up in many different media. Water, light waves, electromagnetic waves, that's radio tower over there, sound waves, and matter waves, people doing the wave. So we're going to touch on a lot of different types of waves this term. This term actually pretty much cohesively throughout it is about waves, except for fluids, oddly enough. We don't actually deal with the wave behavior of fluids, because that's very complicated. Okay, so periodic motion is motion that repeats itself over and over and over again. So we've seen the spring mass system before. Pendulum, we've seen that before. Vibrating strings of an instrument. Those of you who are in the RE program, you know about buoys in the ocean. Those are great generators of energy. Turning fan blade, all of those have periodic motion. And we sort of, under that umbrella term of periodic motion is simple harmonic motion. So it's periodic, but it also has some simplifications, because we love to simplify things in physics. So it's defined as simple harmonic motion basically when there's no damping force. When we can pretend that that system is going to oscillate forever and ever and ever with nothing that's going to decay the amplitude away. So then we have this equation that defines simple harmonic motion. And you'll notice that this is x as a function of time. I've got no y term, so this is actually one-dimensional motion. So really common example we use is the pendulum, or not, excuse me, not the pendulum, a spring mass system oscillating up and down. So if it's oscillating up and down, it's oscillating in one direction, and so that makes a really good simple harmonic motion system. So we're going to define all these terms. So x of t is the displacement as a function of time. X doesn't necessarily require that it be motion in the x direction. If we're using a hanging mass system, then it's moving in the y direction. So x isn't necessarily horizontal motion, it's just any displacement, units of meters. So this is x of t is the displacement from equilibrium. That's an important point, from equilibrium. The amplitude would be the maximum displacement from equilibrium at any given point in time. Not any given point in time. Throughout the whole cycle of motion, A is the maximum displacement. Period is the time it takes to go from peak to peak or trough to trough, the time for one cycle. And so here we have a sine function, and that's what we're going to be dealing with for the next couple weeks, sine function. So our y-axis is x, which is confusing, I realize that. Our y-axis is position, and our x-axis is time. And you might see, instead of A for amplitude, you might see X max used. And then this graph shows, of course, that the period is going to be the time for one cycle. Just pick a point on the sinusoidal curve and find where that point happens again the next time it happens again. Frequency. So we've seen this term before. So period is capital T, has units of seconds. Frequency is defined as 1 over the period. So that would give it units of 1 over seconds, which we call hertz. So probably review. Angular frequency you have seen before. What you saw was, we called it angular velocity. We did rotational motion in 221. So angular frequency and angular velocity are they're the same thing. We just use two different words for the same thing. So angular frequency uses symbol omega, and it's simply defined as 2 pi times the frequency. So that takes it from being in terms of seconds to be in terms of radians. 1 over radians, that is. So it would probably be helpful to refresh our memory about the conversions between seconds, or between degrees and radians, if that needs to come up. So there are 2 pi radians in 360 degrees, which is the same as 1 revolution. So for the car enthusiasts in here, your car's engine is rated in RPM, rotations per minute. That's the same thing as revolutions per minute. So the book loves to give things in RPM, since that's a pretty common measure of performance in a car, or how it's running. So you frequently have to convert from revolutions per minute to radians per second, which you probably remember doing a lot of in 221. All right, the new term that you haven't seen before in physics is phi. This is phase angle. So if you've taken circuits, you've probably seen it before. But this is the new one for us, phase angle. I need somewhere to write it. I guess I'll put it over here. And it's an angle, so of course it's going to have units of radians. And the purpose of phase angle is to denote where the basically where it started when you started your stopwatch. So at time equals 0, where was the motion? The way I drew this picture, I started my watch at the same moment that I let go of my displaced mass. So if this is a spring mass system, I lifted it upwards and let it go at the same moment. So it starts at its peak. In this case, your phase angle is 0. But if you just walked into a room and you saw a spring mass system oscillating up and down, and you go, hold on, I want to measure the properties of the spring mass system, and you get out your stopwatch and you hit start, it's not necessarily going to be at its peak when you start it. And the picture in the book on this page shows an instance where that's the case. So your phase angle would be the distance from a peak back to the origin. So that would be a phase shift or phase angle. Those words are used interchangeably. So usually, to simplify things, we'll usually just let the phase angle be 0. But sometimes they'll throw you a curveball and put a value in there. So that's what it is.
How is it an angle, though, if it's just an oscillating spring in one dimension like that?
That's a great question, and I'm going to skip ahead to a topic that's very much related to that. It won't require any explanation, but it's just further ahead in my notes. So,
okay.
Since you asked it, so relating circular motion to one-dimensional simple harmonic motion. Yeah, because we're like, where's the angle come from, right? If it's one-dimensional. So this is sort of the opposite case, but it's a really good illustration of that. So in 1610, Galileo observed Jupiter with a telescope for the first time. This was like huge. He happened to also observe that Jupiter had moons. At first he thought they were just stars that happened to be behind Jupiter. But he was looking at Jupiter every single night and making observations in his lab notebook. And he noticed that these stars hugged Jupiter. They just moved every night. And so these are actual locations of those stars that he recorded on different nights in 1610. And he was able to figure out that these were 4 moons that were all orbiting at different rates based on their how close they were. And this was just a month of observation. So you know that if you looked at Jupiter from the top, those moons are orbiting in a circular motion. But if you look at that on the side, the moons are going to look like they're going back and forth, like in one-dimensional motion. So, of course, it's weird to think of this spring mass system as having some kind of circular motion. But if we think of the parallel example of Jupiter, then you can understand kind of where they came up with the idea of a phase angle. So you can quantify the distance from the origin in terms of radians. So there's no like visualization for the spring mass system, but this is sort of our parallel case where you can make the case for that. So how they do that for position is, so it's like 2 pictures in one. The circle is the top-down view of a planet or a moon orbiting Jupiter, and just the x-axis is sort of that whole system turned on its side. And so what you're seeing is a projection of that moon on the x-axis. And so as the moon goes around, what you see is that dot on the x-axis moving back and forth. And so the distance along the x-axis is your position as a function of time. That length is going to change as the moon goes around in a circle. The actual peak amplitude is the radius of the circle, and that only happens twice a cycle, just like on our sine wave. The angle then can be measured based on this little triangle that forms at any moment in time. So that's your phase right there. Phase is the whole term omega t plus phi that we see in our cosine function, and then that phi term is just the phase angle itself. So as your moon orbits, that phase is going to change, and you could get a new value for phi for any moment. Actually, the phi would be a fixed number. It's the time that's changing. So, so that's how you could figure out a phi. Even if you don't have a real circular system, you can see a relationship between x of t and a and your phase angle as this triangle that exists. Yeah, Christian?
So would the origin then be the equilibrium point of that? And
yes, that would be like our zero.
Yeah,
yes.
And what would be the difference between the equilibrium and where it's at?
Where it's at, yeah.
Okay.
Well, it's related.
It's related.
Yeah,
okay.
yeah. The actual distance is your x of t, sort of this horizontal distance on the triangle. But it's related just with the cosine function, which is why we have a cosine, because you've got the adjacent side and the hypotenuse. Yeah. So hopefully that kind of demystifies a little bit where we get the term of phase angle from, even though we don't have a circular motion system.
So it's more just about the period of the oscillation.
Yeah,
So,
it's
like from trough to trough or from peak to peak, it would be 2 pi radians, or it would be
your phase angle. It's gonna
not the phase angle itself, but just like you're separating that into like a full rotation type of thing.
Right. Yeah. So that's right. So one full period would be a phase of 2 pi. Okay. This whole term being called the phase. And so we'll come back to this picture in a little bit, but that was really a good question. Usually I skip this slide because it doesn't really further our physics, but it may help the understanding a little bit. Where were we? Oh, here's another equation that's useful. So because we've got frequency is 1 over t and omega is 2 pi times frequency, we can use combine those to get an equation for period in terms of angular frequency. So just having a bunch of those is handy. Okay, so we got our position as a function of time. And if we wanted to get velocity as a function of time, we can just take the first derivative. So I've done that on the overhead. I won't show that again on the board. But if you're thinking about the calculus in your head, we have to do, is it called the chain rule? I'm tired right now. Chain rule. So we take the derivative of the outside, or we take the derivative of the inside, which gives us omega. And then we take the derivative of the outside, which gives us a negative sign. And so that's why we end up with the velocity is negative omega a sine, and then the same phase. This term out front is just like on our x of t, the term out front was our peak value. So our peak value is omega times a. You could also write that as V max. So V max is omega times a. And a really nice way to visualize this is to draw this directly beneath your position graph. So there's our position as a function of time, and our velocity as a function of time. So here's Vmax is omega a. Okay, and so we had a cosine before, and then the derivative gave us a negative sign. So where are we going to start drawing a negative sign function? Do we start at the peak, at the origin, or at the trough?
Origin.
Okay, and am I going up or am I going down?
Down.
Down, yeah, because it's a negative sign. So at this point in time, I need to be here. At this point in time, I need to be back to here. At this point in time, I need to be
Back at the origin.
back of the origin. Okay. Okay. So hopefully that lines up the way it's supposed to. Well, close enough. Did for the first 1.5 cycles, anyway. Growing as I see. Okay, so that way you can visualize the math in the equation, and then this is like just basically taking a derivative. So the acceleration is then the derivative of the velocity function. So if you take the derivative of all this, you get negative omega squared a cosine of the phase. So in this case, our maximum acceleration is omega squared times a. Okay, so I've got a negative cosine function. So am I starting at the peak, the origin, or the trough?
Trough.
Okay. So it's going to look exactly inverted from my position graph. Okay. Okay, so really that just having the pictures along with the equations demystifies the equations. They look complicated, but they're not really that complicated. Okay. So this comes up in one of the problems, so I thought I'd look at this really quick. If we wanted to know what our initial displacement is, all we have to do is throw in time equals 0. And so this would be relevant if we had a phase angle. Then you might not be starting at A max, or A, I should say. So if you plug in time equals 0 into the position equation, you end up having the initial position just be A cosine of the phase angle. If you do the same thing for velocity, your initial velocity is minus omega A sine of the phase angle. So we're going to use, we're going to kind of derive something right now in our groups, and then we'll use it in a few minutes. So try and come up with an equation for A using just our expressions for x naught and v naught. And as a little hint, it might be helpful to use this trig identity, sine squared plus cosine squared equals 1. So if you're not already in a group, John, you might want to join a group so you've got people to work with. So spend a few minutes as a group to try and come up with an expression for A that doesn't depend on the phase angle.